Hello and welcome to this first lecture on linear algebra in our course, A Mathematical Foundation for AI. Today we're going to be talking about scalars, vectors, matrices, and tensors. And this is all presented by EDU Onyx. Hopefully this will be a lot of review for you, and if it is, that's good. You want to have a strong foundation in this because this notation and these vectors and matrices are ultimately what gets used in each and every deep learning algorithm out there today. Inputs are typically passed to these algorithms as vectors or matrices. The outputs are also either scalars, vectors, matrices, or tensors. So when we're talking about dimensionality, again, that comes up a lot of the times in machine learning. That is really going to be a difference in scalars, vectors, matrices, and tensors. And we'll look at a little bit more what that means in a second. This is just the first video. We'll also have videos on matrix normalization, and we'll move on to special matrices and vectors after that, such as diagonal matrices, symmetrical matrices. Also, at the end of this unit, we are going to be talking about eigenvalues and eigenvectors, and that is ultimately because eigendecomposition is used in principal component analysis, which comes up in artificial intelligence as well. So for now, let's go ahead and get started by diving into the basics. All right. So, just starting simple, a scalar is going to be a single number or value, and this is typically denoted with a lowercase variable, just x in this case. And then we can move on to a vector, which is going to be an array of numbers, either in a row or in a column, which is going to be identified by a single index. So here, this is also going to have the notation that you'll probably get a lowercase bolded variable to denote a vector. You might also see it with the bar over the top of the variable. It kind of depends on what context you are in. Some of this has slightly different conventions in machine learning or the computer science world versus strictly the mathematics or the math world. So that's a vector, an array of numbers, and we'll look at plenty of examples in a second. We can move on from a vector and get a matrix, which is going to have two indices now. So it's a two-dimensional array of numbers where each element is identified by these two indices. And this is going to be denoted with a capital and bold variable in most of our lectures here. All right, so we have scalars, vectors, and matrices. And so you can see the trend here. A scalar kind of starts as, you could think about it as a single a point perhaps, no dimensions. A vector gets one dimension, it's now an array, and then a matrix is going to have two dimensions. So let's look at some examples because it's a lot easier to see when you're actually looking at the numbers. Alright, so here on the left we have an example of a scalar, a vector, and a matrix. So the scalar we noted is just any real number, it's a single value. And then the vector now has one indice. So this could be either a row vector or a column vector. You see the row vector on the left, the column vector on the right. Again, since this still only has one indice, it's still considered a vector. However, as soon as you add another indice, you get the matrix. So let's look at the general formula for those. We denoted the scalar with just a variable. The vector here, we start to get indices, and this is really what denotes the difference between a vector or a matrix, is the existence of only one indice, or moving to the matrix, the existence of two indices. And we'll talk more in depth about indexing in a second. So for the vector, we have these indices going from 0, 1, all the way up to n. This is going to be just integers. And then that also holds if you have a row vector or a column vector. Either one is just going to go from 0 to n. And that's kind of convention. A lot of the time in the computer science world, you're going to see that the vector indices or the matrix indices are going to start at 0. Sometimes in mathematics, you're going to have them start at 1. However, since it's more common to see the 0 when you're working on a computer, I'll try to use that notation most of the time. All right, so the matrix as well, we're going all the way from 0, 0 to mn here. So this is in a row column format. And let's take a little bit of a deeper look at that indexing. So rows is going to go downward. These are all the rows across that you have. Columns are moving to the right. So in this scenario, we are going to have n columns all the way from 0, 1, 2, 3, on and on to n. And then we're going to have m rows, 0, 1, 2, 3, all the way up until m. So these can be any size. When you start thinking in the context of computers, you can have matrices that get very, very large very quickly, because m and n here can be very large numbers. So as a result, you're going to have an exponentially increasing size to the matrix. It's something that you got to keep in mind when you're thinking about the computational resources that you have to use in machine learning. So for vectors and matrices, excuse me, which we mentioned, these are typically going to start at 0. You will see them starting at 1 if it's in more of a mathematical context. And then just for an example, the entry at row 1, column 1, is index 1, 1 here. So you see, you might think index 1, 1 would be the very first element in this matrix. However, that's not the case, because it's actually going to be the second row and the second column, since we're starting at 0, 0. And then alternatively, if you thought about it, since rows are going to come first, the index 1, 0 would be just left of that little red box. I'm starting with rows and then columns afterwards. All right, so that's the indexing. Let's talk about the dimensions. Vectors are one-dimensional, matrices two-dimensional, and dimensions are typically reported in a rows columns format. So for example, if we had this matrix, so it has 2 rows and has 3 columns, we would say that this matrix has the dimensions of 2 by 3. Or alternatively, you might hear simply, this is a 2 by 3 matrix, and that 2 by 3 implying the 2 rows and 3 columns. Again, this matrix is very small, and when we start looking at some of these in a computer program, these can grow rapidly and have a wide variety of different dimensions. Alright, so there's the basics of scalars, vectors, and matrices. Let's move on to some of the operations that we can perform. So matrix operations such as addition, subtraction, and multiplication are used all throughout the field of machine learning. These are going to come up almost every single time, and that is ultimately one of the main reasons you have to have a strong foundation in this. So hopefully this will refresh your memory on some of the basics of linear algebra. So matrix addition is just going to be an entry-wise sum. The addition of matrix A with matrix B is going to produce a matrix C. And here you also have to ensure, since it is an entry-wise sum, that the dimensions of A and B must have the same. Furthermore, the matrix that you produce is going to be the same size as A and B. So if we look at this example here, first thing that we can note is that the indexes start at 1. So we talked about a second ago, this is probably more of a mathematical example in a mathematical context. And then, so to get the first element in C, we would simply add A11 to B11, and that is going to give us the answer for C11. And we would do that all the way up to Mn, the last element in our matrix. Let's look at an example with some actual numbers here. So if we had matrix A, which is a 2 by 3 matrix, plus matrix B, which also has to be a 2 by 3 matrix, we would get matrix C, which is simply the addition, and we actually have some errors here. That first element should be 3, so we should have 3, 3, 7, 5, 6, 8. Since we're having a 1 from A11 or A00 plus B00, which is a 2, we should have a 3 in that, so I apologize for that mistake. Matrix subtraction is going to be performed element-wise as well, just like matrix addition. In fact, it's going to work almost exactly the same, just substituting a subtraction instead of the addition. So dimensions have to agree. The output is going to be a matrix of the same dimensions. And here, this is actually our first example. We can have negative numbers in these vectors or matrices. We can also have decimals. We are not restricted in the type of number that we can have in these. So that's matrix subtraction. Matrix multiplication is where we get a little bit more complicated, because this is not just an element-wise product. So the matrix product of A and B is going to be a third matrix C, and instead of having to have all of the same dimensions, now all we need is A must have the same number of columns as B has rows. So if we take a look at this middle image here, we can see that yes, A has the same number of columns as B has rows. It's actually the same dimensions in this example. We'll look at an example in a second where they don't have the same dimensions exactly. So to get the first element in C, C00, we are going to move across a row in A and down a column in B. So that first element is going to be A00 times B00 plus A01, so we're moving across the row, times B10 down the column of B. So it's easy to lose track of where you are in matrix multiplication. Across the rows on A's, down the columns on B. And ultimately that is summarized in this lower image, which would be the matrix multiplication notation. We have Ci of j is going to be equal to the summation of Aik Bkj, excuse me. And so this here, since the k in A and B, this is ensuring that A has the same number of columns as B has rows. And for example, for C00, we would start at A0 and then take k all the way up to however many columns we had. And then we'd start at B, K0, and take k down all the number of rows that we had in B. All right, so that's a lot of indices and down rows and over columns and stuff like that. So let's take a look at some actual numbers, because practice makes perfect, and this will help this make a little bit more sense. So if we have an example where we don't have exactly the same dimensions, we do still need to have the same number of columns in A as rows in B, and that's what we have. We have 2 columns in A in this example, and then 2 rows in B. So we have a 3 by 2 matrix being multiplied by a 2 by 2 matrix, and our output is going to have 3 rows and 2 columns. So however many rows in A that you have, that's how many rows you're going to have in C. However many columns in B that you have, that's how many columns you're going to have in C. And this is following that same matrix multiplication formula. So here's some actual numbers, just multiplying these across. So you would start in the upper left of A, so you have 1 times 1, and then move across the row, so you get a 2 down the column, times 2 in B, and that's going to be your first element in C. So if we add these up, we would get a 5 in that scenario. And then you would simply start going across the matrix. So for example, the C11 element, the C10 element, you would use the same 1 and the 2 from the A, just multiplying now by the 3 and the 4 in column number 2 in matrix B. So that's matrix multiplication. That's an example of that. Hopefully this is a little bit of review. If it's not, we'll have plenty of practice problems for you to go over this further. As well, in Python or R, matrix multiplication is very easy to do, so we'll play around a little bit with how to multiply matrices using those programs. Alright, some properties of matrix multiplication. Matrix multiplication is distributive, so our same multiplication properties apply here. It's also associative. However, it's not commutative, so A times B does not always equal B times A. That is the main difference here, since our dimensions could change depending on which order we multiplied them in. So these properties still hold. That will come up from time to time. It's a good idea to keep those in mind. Alright, so that's some matrix operations. However, arguably the most important matrix operation that we're actually going to come across in machine learning is the matrix transpose. So let's talk about that now. The transpose of a matrix is simply an operator which is going to flip the matrix over its main diagonal. And the main diagonal, of course, is going to run from the top left to the bottom right. So if we look at that here, this arrow is going to summarize the main diagonal running from the top left to the bottom right. And then the indices of the rows and the columns are going to be switched. And so you see here this superscript T, that's how you denote a transpose. It's going to be a superscript T, and you see that in the top right of the first matrix. And then on the right we get the transpose, so the indices are switched. You see along that top row we now have A00, A10, A20. So we're not just switching our notation here, we're actually switching those elements. So we're flipping our rows and columns. And let's take a look at some examples for that, because that will make it easier to understand. So the transpose of this nice 1, 2, 3, 4, 5, 6, 7, 8, 9 matrix here, we're going to flip our rows and columns. So now along that top row, we are going to have 1, 4, 7, which was our column in the initial matrix. So we're switching rows and columns. And we can also do this for a matrix that doesn't have the same number of rows as it does columns. So for example, we have a 3 by 2 matrix here. And if we take the transpose, we are now going to get a 2 by 3 matrix back out. So we're switching the rows and the columns. That's the easiest way to think about the transpose. So in this second example, the main diagonal here would run from the 1 to the 4 in the first matrix on the left. So if you can think about flipping this over that 1 to 4 diagonal, we now get the 3, 5, 6 up on the top, and that 2 would flip down underneath. And that's why we get that 2 by 3 matrix back out. Furthermore, we aren't restricted to matrices actually here. So we can take a vector transpose, and this is going to flip a row vector into a column vector. If you took the transpose again, you would get back the original row vector. In fact, it's a good idea to note that if you take the transpose of a transpose, you're going to get back your original matrice or vector every single time. So this is really useful, this vector transpose, because a lot of the time we have to pre-process the data that we are feeding into machine learning algorithms. And so, for example, our data might be stored in rows and we need to input it as a column or vice versa, and we can fix that by taking a quick vector transpose to get the data in the format that we need to input it into the algorithms that we are using. So the transpose comes up a lot, specifically in pre-processing. However, it will also be used in some layers of deep neural networks from time to time. So there's the matrix transpose. That is very common. However, let's take this one step further, or actually several steps further, and cover tensors. So matrices have two axes, and I hope you noticed the trend in the first slide. We went from a scalar, which had no indices. We went to a vector, which had 1. A matrix had 2. We don't have to stop there. We can keep going. So in general, an array of numbers with a variable number of axes is known as a tensor. So if a 2D matrix has indices ij, a 3D tensor would have indices ijk. So we can keep going and produce a 3-dimensional tensor, and we can even move on further than that and make a 4-dimensional tensor, 5D, 6D, and we even don't have to stop there. So these are getting harder and harder to visualize simply because we are living in a 3-dimensional world. You're probably looking at this on a 2-dimensional screen, and so it's difficult to do. However, a computer can handle this very easily. A 6-dimensional tensor is no more difficult than a 2-dimensional tensor or a matrix for the computer to handle. You will have a much larger number of parameters simply because it's growing in size, so it does get more computationally expensive. However, in theory, nothing changes. So we can have any number of dimensions on these different arrays. We could have a 100-dimensional tensor go all the way up simply using our computers. The computers handle these very well. So there's no reason to stop at the 2D matrix. And that's just important to note because a lot of the times in these machine learning algorithms, you're going to be working with high-dimensional data or high-dimensional layers of a neural network. For example, in deep neural networks, oftentimes you take an input, which is going to be a two-dimensional matrix. For example, if you're using an image as an input, and the inner layers of that are going to have a higher number of dimensions. And so we're covering this because those layers and those weights and those inputs are going to take these structures from time to time. It's a good idea to just understand them fairly well to start, so that when they come up in machine learning, you have an understanding of the actual data structures or the data types that are being used. All right, so that's tensors, and that actually brings us to the end of this first video on scalars, vectors, matrices, and tensors. That was pretty quick, and that was just the bare bones basics, and that's why we're going to supplement this video with a project where we can explore some of these matrices and tensors, vectors as well, using Python and NumPy, which is a computational library for Python. In the next video, we're going to cover matrix normalization, such as absolute value norms, Euclidean norms, and so stay tuned for that because those come up all the time as well. Thank you very much for listening.